There are many industrial activities which could have an impact on the surrounding environment. Some lead to an increase of the pollution of air and water by toxic contaminants, such as heavy metals, nitrates, and plastics. Some toxic substances, such as the ones released by burning fossil fuels, are responsible for ozone layer depletion and cause global warming. In other cases, there is also the risk of the release of radioactive materials to the environment. The first human activity related to radioactivity that you may think about is energy production by nuclear power plants, which directly manages radioactive materials and wastes. In this case, the main concern is artificial radionuclides. Indeed, during reactor operation, nuclear fission is able to produce radioactive isotopes and elements that are not already present in nature. However, there are radionuclides that are naturally present in the environment, and there are other industrial activities like oil and gas industry that could produce contaminant byproducts. Nuclear power plants, like every industrial activity, could have an impact on the surrounding environment. It is important not to jeopardize the safety of people and animals that could live near it. Therefore, there is a constant and rigorous monitoring of the ongoing situation. This is called environmental monitoring. During normal operation, a power plant produces gaseous effluents and liquid wastes, which may or may not be contaminated by artificial radionuclides. The huge quantity of steam that you see exiting the cooling towers is water vapor, and it will not contain any radioactive materials produced by the reactor, but is important to guarantee there is no release of radioactivity. However, in order to avoid any type of contamination of the surrounding area, both gas and liquid effluents are subject to stringent regulations. They are inspected by internal experts and external authorities and are treated, if necessary, prior to discharge via stacks or pipes. These inspections consist of systematic sampling and measurement not only of the liquid and gaseous effluents, but also of the surrounding environment. This includes soil, air, water, seafood, animals, and plants, with a radius of some kilometers from the power plant. They are designed to check compliance with the emission limits set out by the nuclear safety authorities. These limits are set to ensure releases are well within a safe exposure level. A person who spends a full year at the boundary of a nuclear power plant site would receive an additional radiation exposure of less than 1% of the radiation that everyone usually receives from natural background sources. Like other power plants, nuclear plants generate electricity by spinning a turbine. This requires energy. While coal, natural gas, and oil power plants chemically burn their fuel, nuclear power plants exploit the energy produced by splitting atoms. The nuclear fuel is made of uranium atoms that are split in a process called fission. The nuclear fission, initiated by a neutron, produces free neutrons and gamma photons and releases a very large amount of energy. This makes a self-sustaining nuclear chain reaction possible. This energy is used to boil water into steam that turns a turbine that generates electricity. As a result, unlike other energy sources, nuclear power plants do not release carbon dioxide or pollutants like nitrogen and sulfur oxides into the air. Nevertheless, during operation, approximately 300 different nuclides are produced. Although most of them are radioactive, many do not have an effective impact on the environment due to an extremely short half-life, less than 1 day, or to small quantities or biological insignificance. Among the gaseous fission products that could be easily released, there are krypton and xenon. Other relevant fission products are iodine, cesium, and strontium, due to their high production yields. Moreover, they are all highly volatile at high temperatures. Therefore, they could add to particulate matter and spread out as aerosol and gases across large distances. Iodine 131 is the volatile, and in an accident situation, it may be released to air and subsequently be inhaled or deposited on vegetation. It is a concern because when inhaled or ingested, it may be taken up by the thyroid gland and produce significant radiation dose to the thyroid. Cesium is also volatile, but at temperatures higher than those at which iodine is volatile. It has a much longer half-life than iodine and may remain in the environment for many years following a release. Strontium-90 is not released as easily as the other two, but it is a radionuclide of significant biological concern because it behaves biochemically similarly to calcium, accumulating in the bone when ingested. Since milk is susceptible to strontium-90 contamination, this is a particular concern for children who drink a considerable amount of milk. Due to their very long half-life and high radiotoxicity, if taken into the body, especially if inhaled, plutonium isotopes are radionuclides that require special attention. Moreover, neutron interactions with other elements present inside the reactor lead to the formation of activation product. Relevant gaseous activation products include carbon-14, nitrogen-16, and argon-41, while liquid and solid waste could contain chromium-51, cobalt-58, cobalt-60, and iron-59. Tritium is produced as a result of both nuclear fission, ternary fission, and neutron activation of deuterium. One significant source of gaseous tritium is the interaction of high-energy neutrons with boron used in the reactor. Keep in mind that all these radionuclides could be released as a consequence of a nuclear accident. Typically, the radioactive emissions from operating nuclear power reactors result in insignificant doses to the general population. And concerning radiation exposure in residents, the average radiation dose of whole body exposure was estimated to be far below the limited dose, 0.1 to 6.2%. This is evaluated by continuous environmental monitoring. Within the nuclear industry, uranium mining and milling activities also produce radioactive waste, like any other metalliferous mine. The radioactive wastewaters and mill tailings contain natural radionuclides such as uranium, radium, thorium, and polonium, of course at higher concentrations. There are also other industrial activities that, although they are not directly related with nuclear activities or the use of radionuclides, could lead to the production of dangerous radioactive materials and their release into the environment. Human activities such as manufacturing, mineral extraction, or water processing can enhance concentration of natural radionuclides, leading to the production of dangerous radioactive byproducts. These are called technological enhanced naturally occurring radioactive materials, so-called TENORM. Technologically enhanced means that the radiological, physical, and chemical properties of the radioactive material have been concentrated or further altered by having been processed, or beneficiated, or disturbed in a way that increases the potential for human and or environmental exposures. The primary radionuclides of concern in petroleum industry waste are radium-226 and radium-238, which result from the radioactive decay of uranium-238 and thorium-232, respectively, and their associated decay products. The primary radionuclide of concern for the gas industry is lead-210, which forms deposits inside the pipes and equipment containing natural gas. Among the contaminated byproducts, there is the water brought up with the produced oil and gas, filters and sludge deposits. Also in this case, it is necessary to control the disposal of wastes and filters that may lead to an hazardous exposure of workers and the public. Radiochemistry supports these industrial activities in order to detect the presence of radionuclides and evaluate their concentration, thus establishing if they represent a hazard for people or the environment.